The next concept I'd like to introduce is that of scores. Now if you examine the plot we have here, you'll see that it's the scaled data overlaid by the principal components, the eigenvectors. Now we could take this one step further. We could multiply the loadings by the scaled data, which would re-express the data in terms of the principal components. In PCA terminology and jargon, this is called the scores. Now you'll hear scores mentioned in the built-in R procedures that help you do PCA as well as the literature. So it's important that you understand what that actually means. If we look at the first few lines of the scores matrix, you'll see that there'll be 100 rows and the data is now in terms of the principal components. Now it's natural to want to plot this information to see what this does. Now let's go ahead and do that. What you'll see is that the data has been rotated, and the x-axis now is the principal component, the y is the second principal component. The first one accounts for 98% of the variation. I think you can see that the scales make that obvious, but so do the lines. So the red line is PC1, the green line is PC2. What I've accomplished here is a poor man's biplot, which is the next topic we'll talk about. But what I want you to take away from this is that the relationship between the data points has not changed. The orientation has, because we've re-expressed the data in terms of the principal components. This is known as the scores. The next topic I'd like to introduce is that of the biplot. This is the primary visualization tool in principal components analysis. You see these plots frequently in research papers, textbooks, and more generally any literature referring to PCA. Now the bi in the biplot comes from the fact that we plot the scores and the variables on the same graph. It's important to remember that we plot the scores as points and we plot the variables as vectors. This allows us to see the relationship between the scores and the variables, as well as the relationship between the variables themselves. So now I'd like to generate the biplot for you. If you look at the existing plot, I have sort of a biplot here, but it doesn't have the variables displayed as vectors here. So I want to go ahead and clean some things up for you and build this in steps. That way you can see what's going on. So the first thing I do is plot the axis. The red corresponds to the first principal component, the green corresponds to the second principal component. Alright, so in this case I'm going to plot the variables as vectors. We can see here that we have two vectors, each corresponding to the variables in our data set. Now you may wonder if there's a relationship or if there's a meaning behind the direction and magnitude of these vectors, and the answer is that there most certainly is. In particular, the angle between these two vectors, the cosine of the angle, matches the correlation between these two variables. So if we look at a correlation value in the original data, we'll see that it's 0.95. We sort of already knew that when we plotted the data originally. So this angle is very small, meaning the correlation is quite large here. If the statistical or the statistic vector were in an opposite direction, we could say that it's negatively correlated with the physics score. I'll talk a little bit more about this in a moment when we get into the interpretation, but I thought I'd point that out now. The next step is to plot the scores. Now, what we have are the record numbers associated with the original data. So for example, if you see 75 here, we can go into the original data set and look at the 75th row. So this corresponds to the student, the 75th student, who had a grade of 44.2 in physics and 51.3 in statistics. So this is basically the biplot. Now the standard R functions have an object, or have a method rather, that will generate this for you. So what does this all mean? Now, in looking at this biplot, I think intuitively we're drawn to the points in the direction of these two vectors. I know that I am, and I think most people are. So let's examine some points that are near these vectors. So I'll take a peek at record number 7. Now again, the variables themselves are highly correlated here. So we would expect that if one did well in statistics, they would do well in physics. And the proximity of the point to these vectors does in fact show that. So let's take a peek at the 7th row. What we'll see is that the student made 70 in physics and 71 in statistics. Now I'm assuming this is the 0 to 100 grading scale. There might be a curve here, I'm not sure. That's kind of a C, I think. But if we see that 7 is here, it's closer to statistics than it is to physics, which shows us that the physics score is slightly less. If we look at the second record, see the number 2 next to the physics, we'll see that the score is slightly higher in physics than it is in statistics. Now, if we look in the opposite direction, for example 63, I would expect to see a very low score in physics as well as statistics. And let's see if that intuition pays out. Yes, it's a pretty bad score. It's almost equal, in fact, the closer it is to this line. So what we're seeing here is the points over here are higher, okay, because they're in the direction of the variables. The points over here are lower, but the overall conclusion is that they trend together. Okay, we don't really see a deviance, a major deviance between them. Now, we've been looking at the continuum or the range on this PC1 axis from this side basically over to this side, and now I want to focus on the PC2. So we want to look at the data up here versus the data down here. Now there appears to be more data down here than there is up here. I think that's true, certainly from a visual point of view, but let's try to figure out what's going on. So if we look at the 64 value, we might expect the values to be lower than over here, the physics and statistics score. But since it's up here, I would expect the physics score to be higher than the stat score. And let's see if that is in fact the case. Well, that is true. And what we're seeing is that the difference between the two scores is larger than the differences in the scores we see here. Okay? Now, on the flip side, if we look at 75, right, we'll see that the statistics scores are actually higher, which makes sense. Okay, now if we looked at something like 18, we would see that moving this way, and moving down this way and moving this way, down the second component, across the first component, we see that the scores are kind of low, but they are almost the same. Okay, so in the first component, what we're seeing is that the data vary together. In the second, they vary together, but there is a larger degree of variance in the scores. And the second component separates those who do well in physics but not so well in statistics. And this side of the graph sort of shows the flip, right? So in general, you would expect a student who's good at physics to be good at statistics, and for the most part that seems to be true. That, in other words, I shouldn't say good, you would expect their scores to be similar. And that's what's happening in the first component. In the second component, it seems that there is a difference. Okay, it's not much, but it's maybe something that you would want to pay attention to. Okay, let's wrap this up. As you know, this was a manual example of how to accomplish principal components analysis. This is not something you would normally do, as in the real world you would pick one of the R procedures designed to do the PCA for you. However, you still would need to know about the terminology. You would still need to know if the data needs to be scaled mean-centered or scaled to unit variance. You would need to know if the covariance matrix is being used or the correlation matrix is being used. Now, the loadings that we talked about are computed, and these are the coefficients of the principal components. This shows how the variables relate to the component. The scores are the product of the loadings and the scaled data. Essentially, it's the transformed data. So if you plot that, you're going to see the original data in terms of the principal components. Now, ideally, what you're going to find is that the data displays some patterns that you didn't initially observe. This can further be aided. This kind of understanding can be realized using the biplot. The biplot is the primary visualization tool of PCA because it allows us to display the scores while also displaying the variables as vectors. In this fashion, we can see the relationship of the points to the variables as well as the relationship between the variables themselves. Now, I'm working on a part 2 to this video, which will use R functions to accomplish much the same thing. I will use the same data to maintain continuity so you can see how the R functions handle the same data. So thanks for watching.